Hello students, in our last lecture we have studied about universal law of gravitation and we have obtained its vector form also. Then we have studied a special case of a spherical shell. Remember students, for a spherical shell, if any mass is kept outside the shell, then the force acting on this particle due to this sphere is given by universal law of gravitation. Fp is equal to g m into m upon r square, means force acting at point P is equal to g mass of the particle at point P into mass of the spherical shell upon distance between them, square of that. Also we have studied that if the particle is inside the spherical shell, then force acting on that particle will be 0. So remember these things. Now today we are going to study about topic number 8.5, acceleration due to gravity of the earth. Students, we know that any object falls on the earth due to gravitational force of the earth, and so the acceleration produced on that object which is falling on the earth is called a acceleration due to gravity. Now students, here we will consider earth to be made up of a solid sphere and it is having a uniform mass density. We know that in actual case earth is not a complete sphere, its shape is oval like this, but here we are going to consider earth to be a complete spherical solid. Also, the density of the earth is not same everywhere, because we know that earth is made up of mountains, sea bodies, that is water at most of the parts. So densities of the earth at different parts is different, but here we will consider the earth to be of uniform mass density. Now for a point P outside the earth, you can see here this is a point P where a small mass m is kept here. From the center of the earth the distance is small r. This is the radius of the earth, and we know that when any point is outside the earth, the whole mass of the earth is imagined to be concentrated at its center. So mass of the earth is considered to be at its center. Now if we apply the universal law of gravitation, then we get force acting on m is g m me upon r square. Here the condition is r is greater than re, means this distance is greater than the radius of the earth. So in that case the force is given by universal law of gravitation. Now suppose a point P is lying inside the earth. See the figure. This is earth, radius of the earth. Now point P is lying here. It is below the earth at this much depth. This d is a depth. From the surface it is at this much depth and this mass is kept there. So now what is the force acting on that mass due to earth? Now students, here we have to imagine earth into its two parts. One part is of radius small r, a solid sphere, and the remaining part will be this part, that is a spherical shell. Students, if this part is not there, this solid sphere of radius r is not there, then this will be a spherical shell only, and this point P lies just below the spherical shell. That is, we can say that it is inside the spherical shell. So due to this part, because this is also having mass, this is a part of the earth and it must have some mass. So due to this mass, there will not be any force acting on this particle at point P, because it is inside the shell, just inside the shell. So now what will happen? The force acting on this point P will be due to this mass, which is a part of the earth only, because this point P is on this solid sphere and its mass is m. The mass of shell is m dash, but due to this mass no force is acting on this small m, but due to this mass the force will act because it is lying on the surface of this solid sphere. Now here we have imagined the total mass of the earth to be made up of mass of the sphere and the mass of the shell. I have written here, no force acts on the mass m due to the spherical shell at point P, because it is just inside it, and that we have studied in our earlier lecture. Also in this lecture I have shown before starting this topic. Now as this mass m is on the sphere of mass capital M, the force acting on it is given by F is equal to G, mass of the particle at point P, mass of the solid sphere, and upon distance square. So here we have applied universal law of gravitation. Now students, what I did here, I have multiplied and divided by small r. So this r square will become r cube and this r is here after multiplying and dividing. Now density of the earth, rho is equal to total mass upon total volume of the earth. Mass of the earth upon volume, volume of a sphere is 4 by 3 pi r cube, but here volume of the earth is there, so there is a radius of the earth cube. Then here we know that 4 by 3 pi they are constant, so we can write this, that density is proportional to, if we remove the constant then we can put proportionality sign, and what is remain now here, me upon re cube. So we can write this, that density is proportional to mass upon radius cube. So if we consider the total mass of the earth, then there will be radius of the earth, and if we consider mass of that solid sphere m, then we have to consider that radius of mass m. Once again look here, if we consider this much mass, then that radius. If we consider complete sphere, then its mass is mass of the earth, and then we have to consider that radius. Density is constants. Here density is constant, that's why this is equal to this. So it is clear that in place of m upon r cube, we can put me upon re cube. That's why. Now in our next step, what I did, in place of m upon r cube, I kept me upon re cube. Rest of the things as it is. So this is the formula for the force acting on the particle of mass m below the earth, which is at a distance r from the center of the earth. Now for a point P on the surface of the earth, we have seen the case when the point is lying outside the earth, when the point P is inside the earth. Now you can see this point P is on the earth. So if any point is on the earth, then we know that the whole mass of the earth can be considered at its center. So one mass is mass of the earth, other is m, and distance between them is re. So applying universal law of gravitation, we can write force F is equal to G m into me upon re square. Now students, according to Newton's second law, F is equal to ma, but in place of a, here we are writing G, because here the acceleration is due to gravity, and so symbol is used G. So now in place of F, if we write mg, and then m will cancel on both the side, so what is remained here? Small g. And here on right hand side is G me upon re square. So this is the formula for the acceleration due to gravity on the surface of the earth. And we know that if we put these constants, because we know G, value of capital G, mass of the earth is known, as well as radius of the earth is also known. So if we put all these constants, we will get value of small g equal to 9.8 meter per second square approximately. So students, remember this formula. This is the formula for acceleration due to gravity on the surface of the earth. Now let us find the acceleration due to gravity below and above the surface of the earth. Topic number 8.6. So now first let us find the acceleration due to gravity above the surface of the earth. We are going to obtain its formula. So students, you can see here there is a earth and point P is selected here, which is at a height h from the surface of the earth. So we know that when any point is outside the earth, the whole mass of the earth is considered to be concentrated at its center. And here this re is the radius of the earth. So now, according to universal law of gravitation, if any mass is kept here, then the force acting between this mass of the earth and this mass which is at a distance from the center. This is the distance from the center, and that distance is nothing but it is radius plus height. From the center, this distance is nothing but it is radius plus height. So distance square we have to take re plus h square. I hope you understood this. So directly now we are going to write the formula for acceleration due to gravity at height h. Students, this is not g into h. It is g as a function of h, means gravity at height h. So directly writing that formula, we get gh is equal to g mass of the earth upon distance from the center, which is re plus h, and its square. Students, once again, this is the formula of force, and this is the formula for acceleration due to gravity. You can see these two formulas and compare. If there is no m, then it becomes formula for g, means for acceleration due to gravity the mass of the earth is considered, mass of the object is not taken, and that's why we are directly writing this formula gh is equal to g mass of the earth and distance square. Let us give this equation number 1. Now on the surface of the earth, g is equal to gme upon r square, that we have already written here. Let us give this equation number 2. Now comparing 1 and 2, means taking ratio of equation number 1 and 2, on left side we'll get g as a function of h upon g, and on right hand side we'll get this upon this. But common thing, gme will cancel, and this term which is in the denominator will be in the numerator, and this will give the term at denominator. So sit with a pen and a paper and take the ratio and simplify. We will get gh upon g, this upon this, is equal to this upon this, but these two are cancelled, so we will get this on the right hand side. Now next step, if we take this re outside, as it is square, when we take it common outside it will be r square. Then what will remain inside? 1 plus h upon r square will remain. In numerator it is as it is. So writing this denominator term in this form, then next what can we do? R square will cancel. So what is remain now? This 1 plus h upon r square, which is in the denominator, and we know that if we have 1 upon x square, then we can write this as x raised to minus 2. So here also this term which is in the denominator and it is having square, we can write that as 1 plus h upon re raised to minus 2. Now students, how we obtained this term from this? It is quite simple, but still I'll show you. we have this re plus h the whole square, and we want this. So students, just look here, re plus h. If I multiply re and divide re, then it makes no difference. So we can do this multiplying and dividing. Now if I'll bring this re inside the bracket, this re which is in the denominator, if I'll bring inside the bracket, what will happen? I'll get re, which is this as it is, and in the bracket re upon re. This re is inside the bracket, so it will be divided in both these terms, plus h upon re. But re will cancel, so what will remain here? Only 1. So we get 1 plus h upon re. But students, here there is a square, so if I put here square, then here also there will be a whole square, and if I open this bracket, then I'll get re square, which is here, and 1 plus h upon re square. So this is a simple mathematics, and you can apply this. Now students, we obtained gh upon g is equal to 1 plus h upon re raised to minus 2. Now just make the subject gh, because we want the formula for that, acceleration due to gravity at height h. So this g will be multiplied here, so it is here. Rest of the things on the right hand side as it is. So this is the formula for acceleration due to gravity at height h, but we want to make it more simple. For height which is not much larger than the radius of the earth, the height which is not much larger than the radius of the earth, in that case, using binomial theorem, we can write this formula as simply gh is equal to g into 1 minus 2h upon re. In simple way, you can remember that when you use the binomial theorem for this condition, if you use binomial theorem for this condition, then you can write this step by simply remembering that this minus 2 is just multiplied here in second term. Minus 2 is removed from here and it is placed here, you can see. So in this way you can remember, no need to apply the binomial theorem, but you have to write this, that for this condition and using binomial theorem we get this equation from this. So this is the formula for the acceleration due to gravity at height h from the surface of the earth. Now next formula is for the depth. Look here in figure, this is the earth and its surface. Now a point P is selected here, which is at a depth d from the surface of the earth, and we want to find acceleration due to gravity at this point, which is at this much depth. So now students, we know that we can consider this as a solid sphere which is inside the spherical shell. In our earlier topic we have studied about this, and we have obtained the formula for the force, acting on such particle which is at this much depth? Let me show you. Here for this topic we obtained the force F acting at depth is given by this formula. G M M that is mass of the earth, Re cube where R is the radius and R is the distance from the center. So that is force. But if we write this equation in the form of G, then we have to remove this mass. If we remove this mass, then that will be the formula for G. So using this formula, in this case for the depth, directly we can write G as a function of depth is equal to G ms, which is mass of this solid sphere, upon its distance square. Once again students, we know that this part is like a shell and it will not affect the mass at this point P, but remaining part of the earth, that is this sphere whose mass is ms, here we have denoted that mass is ms, so that ms will be now at its center, and so this mass at this distance will act the gravitational force on that particle, and due to that there will be a acceleration due to gravity, and this distance will be how much? It will be radius, this much distance will be radius minus d, so re minus d. Once again, this distance will be re minus d, and that's why we have written G as a function of depth is G mass of that sphere and distance square, distance is re minus d square. Now next step, we can write this as this that I have shown you. Here you can see in terms of mass of the earth we can write in this way. If we want this formula in terms of G, then simply don't consider M, so it is G mass of the earth, radius of the earth and distance. So here in our case this distance is what it is, re minus d. So simply in place of this r we are going to write this, and we get this formula. So students, I hope you understood this. So after writing this step, we can directly write this: G mass of the earth, radius of the earth cube and that distance. So just compare it. I hope you will be able to understood this. Now let us give this equation number 1. Now we will compare this equation with the acceleration due to gravity which is on the earth's surface. Equation number 2. This is the acceleration due to gravity on the earth, which we have done for the height also. See, here also we have written this equation and compared in case of height. So here in case of depth also we have written this. Now we will compare equation number 1 and 2. Compare means we will take the ratio of both these equations. So GD upon G. On left hand side we'll take GD upon G, and on right hand side this upon this. So what is common here? G will cancel, ME will cancel, and here it is RE cube, and here it is RE square. So this RE square will cancel, and here cube will cancel, but one RE will remain. So on right hand side, RE minus D upon RE is remaining. So do paperwork for this, and you will get GD upon G is equal to RE minus D upon RE. Now just separate these terms, that is reverse process of LCM. Let me show you. We can write this as RE upon RE minus D upon RE. RE will cancel and remain is 1. So it is here. And here D upon RE, which is here. So after this step we can write this like this. Now finally what we have to do, we have to just make the subject GD. So making the subject GD, this G will come here in the numerator, and so we get this formula. So formula for the acceleration due to gravity at some depth from the surface of the earth is GD is equal to G into 1 minus D upon RE. So students, I hope you understood about the acceleration due to gravity above the surface as well as below the surface of the earth. But I will advise you to sit with a pen and a paper so that you can do some mathematical work with me. Still, if you have any doubt or any difficulty in the mathematical step, then you can ask me.